Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's a great pleasure to have Philipp Hennig here. He's currently at the Max Planck Institute in Tübingen. We also have a bit of a history together. I had the pleasure of co-supervising Philipp's PhD thesis together with David McKay.
Yes.
We didn't get to see much of David, at least I didn't.
I didn't either.
So, in that work, Philipp was tackling various challenges in approximate inference, also with applications to computer Go and game tree search. And today he's going to talk about the Bayesian framework for global optimization.
Thanks a lot, Tori. Thanks a lot for having me. It's great to be back at Microsoft. I'm going to be talking about joint work with a PhD student called Christian Schuller, who is also with Max Planck in Tübingen. With this place which is now called Intelligent Systems, so this is the institute that Bernard Scherkoff is at. If you're used to biological cybernetics, the name has changed. So I know the faces of most people in the room. I just want to briefly check. So this is a talk about optimization, and there might be, so optimization is a broad field that interests hopefully a lot of people, so I just want to check what sort of audience are, especially sort of the back rows are there. If I'm going to use the term Gaussian process, how many of you will not know what I'm talking about? Very good. Great. So that's going to make things easy. Okay. So I will talk about optimization. And optimization is, as I said, a broad field, interesting to lots of people. It has been discovered and rediscovered in many different fields. So I think it's important to make clear at the beginning what kind of problem I'll be talking about. This is the setup. This is a domain which ranges from, well, in this particular case, from -3 to 3. And I've plotted it in one dimension because it's easy to plot in a one-dimensional or two-dimensional screen. But you should imagine that the problem might be high dimensional, of course. And what you see here are 3 crosses, and these are supposed to be evaluations of a function. And we might have evaluated this function with noise. We might have gained information about the derivative of the function at these points as well, but we don't have to. And you may imagine that we got these numbers by maybe running a physical experiment, doing some tests, drilling holes in Siberian soil, something like this. And the question is, where's the minimum of that function? And so now if you think about this for a while, then the first thing you realize is that it's impossible to answer this question without having a prior belief over what the function is. Because if you don't have that, then for any uncountably infinite family of distributions that you can give me that has its minimum at any of these points, I can give you another uncountable infinite family of distributions which has its minimum somewhere else, and then we get to argue about which of our two sets is larger uncountably infinite. So that doesn't make any sense. The only way to do that right is to assign a measure to the space of solutions. Nice and dark. And I've done that here. So I'm choosing a particular prior, a Gaussian process, and I've already checked everyone knows what that is. That's great. And once we have that distribution, we can now start to think about where the minimum is. And before I do that, before I tell you what I'm going to do, I'd first like to give you an idea for how this works in the current state of the art, at least as far as I understand it. There's basically 2 classes of algorithms, if you want to be very broad and high level. The one family of algorithms doesn't use a prior belief over the functions. So that's the family that involves genetic algorithms, stochastic gradient descent, these kind of things, and a lot of maybe more exotic algorithms like the ant trail algorithm and the beehive algorithm and the leapfrog algorithm and all these things that come out of operations research. So those algorithms, to my mind, are not necessarily optimal. They have all sorts of defects. And there's another class of algorithms which does use a prior distribution and then constructs some heuristic which tells you something about where interesting regions of the function are. Here's one particular one, maybe currently the best or the state of the art. Maybe there's some other ones which are close and similar in their results. This is the expected improvement heuristic. It's actually already quite old. It's 30 years old now. What this is, so this green line is the expected drop in your best function value so far if you evaluate at a certain point. So if you look at every point at the marginal one-dimensional distribution over the function values there, we have a current best guess, which is this one here, and then let's say if we evaluate here, then we expect to be this much better than before on some arbitrary scale, so this green line is a different scale than the function. And then the algorithm would evaluate at wherever this function is maximized and hope that that would get us quickly to some good function estimates. So there are two things wrong, or at least questionable with this approach. The first one is that this green line is not actually our belief over where the minimum is. Our belief over where the minimum is actually looks like this. So I've constructed this blue line by sampling 1 million functions from the GP, binning them on a 100-point grid and building up a histogram. And you can see that, yes, this blue line has something to do with this green line, but it's not the same thing. In particular, there are some global features of this which you cannot get by just having a local view on the function. For example, these edge effects here, so that this blue line moves up here and it moves up there. And intuition for why this happens is, so this particular GP prior that I've chosen has a kernel which induces beliefs over functions which are smooth. So therefore, at the edges of our region where we think the minimum is, the function has with a finite probability a negative derivative. And in those cases, and there are finitely many or there's a finite mass of them, there's a sort of an open region around the boundary of the domain where all the mass for the minimum moves to the boundary, right? Because if the function has a negative derivative, then the minimum has to be over there. And that's something you can't capture with a local concept.
But somehow the heuristic seems to have picked up on the edge as an interesting area as well. Is that just
well, it has picked up on it because there's a lot of uncertainty here. So there's just each of these points has a finite probability to be. Well, actually, this just has a nice expected improvement. It's not really a probability relative to all the other points. Well, this blue distribution is an actual probability distribution over where the minimum of that function is. There's another thing wrong with this approach, and that is that while this may be, well, actually in this case it isn't, but it might, even if this may be the point where the minimum is most likely to be, that's not necessarily the right point to evaluate. Because we're trying to learn about the minimum, not to hit the minimum. And trying to learn about so if you want to learn about the minimum, then you should evaluate where you think you're going to learn most about where the minimum is, not where you think the minimum is. So I'm going to try to address all of these points in this talk. And so I'm first going to set up the idea of what I would like to have. This algorithm will turn out to be hard in many different ways, and then we'll have to find approximations for each of these problems. But here's the optimal algorithm that I would like to have. It starts by assigning a probability measure over the functions, and I've already put a tick mark there because I've already decided how to do that. I'm going to use a Gaussian process prior. Partly because it's the only prior over functions that you can actually do anything interesting with. And if you're doubting the utility of Gaussian process priors for optimization problems, then ask me again at the end. I have some ideas for how to maybe address your worries. Now, once we have this measure, then this measure implies a belief over where the minimum of that function is. It implies it, but it's not necessarily easy to evaluate it. So we'll have to figure out how to evaluate it. And this will be hard in two ways. It'll first be hard because even in a discrete setting, this will involve an integral which has no analytic solution. And then we are also thinking about a continuous function. So this is actually sort of an infinite dimensional problem. And we'll have to deal with that as well. Then once we have this belief over where the minimum is, we'll have to turn this belief into a number which represents our uncertainty over where the minimum is. And the classic concept for that is entropy, or some concept that is somehow close to entropy, because we're in a continuous domain, and I'll talk about that. And then we will have to predict how this entropy changes, so how much information we gain by evaluating at some point. So we'll need a model for how our uncertainty is expected to change as we evaluate somewhere. And then finally, usually in optimization settings, you have more than one more evaluations to go. So your manager may have told you that you're allowed to drill 10 holes into 10 boreholes into the Siberian soil, or to kill 50 mice, or to do 20 medical experiments, something like this. And then the right thing to do would be to optimize up to the full horizon over those 20 or n steps. And that is a hard problem. It's a dynamic programming problem. And we know that these problems are hard, exponentially hard, and the solution is dynamic programming. But we also know that optimization problems are, in some sense, benign to this problem, in that you can't really get stuck. So in a general MVP, Markov decision problem, you might be unlucky to do something silly early on, then you can never get out of it anymore. In optimization, that's rarely the case. So you usually, especially with the GP, which is an exchangeable measure, you can just, if it turns out that one of the evaluations wasn't that great, you can just evaluate somewhere else. So while you won't be optimal, at least you won't be really bad. So this is why there's a little cross here. I'm not going to address that point, I'll just be greedy at every step, which is why this talk is called information greedy optimization rather than information optimal optimization. Okay, so now we'll have to go through these points, one after another. I'll start with the first one. I said that even for a discrete setting, so if you now for a moment assume that we just have discretely many points on which we're trying to consider where the minimum might be, then our belief over the minimum, if we have a Gaussian process prior, so then our belief over the function is finite dimensional multivariate Gaussian distribution, then the probability for the kth location to be the location of the minimum is the probability that the function at location k is less than the function at any other location, where this theta here is Heaviside step function. This kind of integral is an integral over a multivariate Gaussian distribution over a half-open, piecewise linearly constrained convex domain. And these integrals are known to be very hard to evaluate analytically, but fortunately, thanks to some of the people in the room today, we know how to evaluate this integral approximately quite well. To be precise, that's thanks to Tom and thanks to expectation propagation. What this integral is if you think about this in terms of a factor graph, is we have some belief over the function, and there's a number of constraints that says the function value at location k is less than at all the other points, and we're interested in the normalization constant, so the mass of the marginal over this function under these constraints. For people at Microsoft, you might think about this as sort of the core part of true skill, if I may. So you have n players playing against each other in one game, and you want to know which of them is the best one, or the worst one. So I'm sure I don't have to tell you here how to run EP, so we can do that, we can do it efficiently. It's still not really cheap. It's actually, even if you do smart when one updates, evaluating this probability for every x in the domain is quartic in the number of points. So it's not cheap, but it's also still doable. And if you do that, then we get this kind of picture. So this is the same plot as before. We still have the green and the blue line. The blue line is what we would like to have. And the red dashed line, which you can probably barely see because it overlaps almost perfectly, is the result we get from EP. And there's one little region here where it's doing not so well, and then overall it's a little bit too low because of this error over here. But I think this is still quite a good approximation. It's definitely a much better approximation than the green line. And the other advantage is that it provides us with an analytic belief we can take derivatives of. And we're going to need that eventually. Now, if you think about this plot for a while, you'll notice that this is maybe a bit of a dangerous way to look at this problem, because I'm still doing these one-dimensional plots. And in one dimension, yes, I can easily just select 100 points and put them on a grid, and then you'll get this nice smooth red line, and it'll look like everything's fine. But even already in a two-dimensional problem, I can't use this regular grid anymore, because then if I want to have the same resolution, I'll have 10,000 points, and in 3 dimensions I'll have 1,000,000 points. And I just told you that EP is quartic in the number of points, so this is certainly not going to work for a higher dimensional problem. Yes?
Just a question. This little spike that you have there on the side.
This one here?
Yeah, its width, is that
No, so yes, so the width here is just because I've discretized the space.
That's really just a spike.
It's really just a point spike.
Or now, would that spike, I mean, suppose you took a square support, would there be like a little wall along the sides and then a spike in each corner?
Exactly.
Right.
But of course, only as long as you don't really know the derivative of the function in this region. So if you evaluate it close to it and you know that the function moves up here, then the spike will suddenly drop away. Okay. Yes, so now we'll have to somehow make this still tractable for higher dimensional problems. So, okay, so I already told you that the first idea you could have is to, well, just have a regular grid, as I just showed you, and then run EP on that. That's not going to work because it doesn't scale with dimensionality. But there's also another sort of problem, it's not really a problem, but there's an inconvenience in that that's actually not the optimal thing to do, because it will put the same resolution everywhere in the space, and in particular also in regions where we already know that the minimum is very unlikely to be, or that we know that the distribution may be very homogeneous, and then it's not really necessary to put that much resolution and in an area that's not interesting anyway. The optimal answer would involve assigning the evaluation points, these finitely many points that we have to approximate our distribution, using the actual natural measure, which is the distribution over the minimum. But that's a circular definition, so we can't do that. Right? We can't use the function we're trying to evaluate to decide where we're going to evaluate it. But we can do something that gets close to it. We can choose another measure which tends to have high mass in about the right regions. And that's why I've left this green line in all the time, because it is actually not entirely bad, right? It sort of puts mass at the right point. So we're going to use that to decide where to put our discrete locations, our finitely many discrete locations with which we're approximating the actual function on this continuous space. We'll just sample from this measure. It's not actually a normalized measure, but that doesn't matter because the normalization constant will drop out of all the calculations. And then you have to be a little bit careful how you evaluate like what the actual probability density in the end is going to be, because we're sampling from a non-uniform measure. So that's what this math down here is supposed to say. Basically, you just have a finite number of discrete points over which we have a probability distribution. And we want to have a probability density in the end, so we have to take care to get the measures right. But this just works if you do it right. Okay. So that gives us a handle on the distribution over the minimum, the belief over the minimum. It's already approximate, and it's sort of approximated by finitely many points and so on. But we can do this such that at least the algorithm doesn't have a computational bottleneck with dimensionality of the problem. Of course, if the problem is high dimensional, then the resolution will be bad, because we only have finitely many samples, but at least it won't run slower. Now we need to move to the next point and somehow construct from this distribution a number. So we need some functional that turns a distribution into a measure of uncertainty. And, well, I already told you that evaluating the maximum is not a good idea. Instead, we want to maximize predicted information gain. In discrete settings, where you have finitely many points, most of us will probably agree that sort of the accepted measure of uncertainty is entropy. So the negative expected value of the logarithm of the probability. And so there's a famous little story that in one of his original papers, Claude Shannon actually suggested that the right measure for uncertainty on a probability density is to just replace the sum sign with an integral, and then you're supposed to be done. But that's not a well-defined operation, because probability densities have a unit of measure, while probability distributions don't. So this P of x actually has the units 1 over x. So what we have in here is a logarithm of a quantity with a physical unit, and that's not a well-defined operation. It's not conserved under changes of the measure. So instead we need something that does transform properly, and well, a lot of people, in particular Edwin James, suggested that the right measure for uncertainty is relative entropy in continuous spaces, because that does transform properly. Relative entropy is also known as scalar divergence, from some base measure. And you can interpret this base measure as a prior over where you think the minimum is, some other source of information about the minimum. So I'm going to choose, for simplicity, that measure to be a uniform distribution over this bounded region in which I think that the minimum lies. That makes things particularly easy. If you want to have some other measure, in particular if you have an unbounded region, then you have to think about how to have a proper measure. Then you can still do this, but things become a little bit more complicated, because you can imagine that if you have a prior over where the minimum is, that prior also tells you something about what the function is. So if you think that the minimum is more likely to be here than over here, then you're essentially saying the function is more likely to go down here or to have a lower value here than over here. So you have to take care to do that right, which can be done approximately, but I'm not doing it here. And then, so this piece of confusing math down here is just to suggest that because we're approximating this integral with finitely many points, you have to be a bit careful again to get the measure right with our discrete numbers and do everything right. But it can be done, you just have to be careful to have the right numbers everywhere and you get the right results. Okay, so now we have a number which tells us how uncertain we are. Now we need to predict how that number is going to change as we evaluate somewhere. And this is where the fact that we have a Gaussian process prior comes in very handy. It turns out that the expected change of a Gaussian process belief under evaluation at any point on the domain can be constructed analytically, and it actually is itself a sample from a Gaussian process. So the Gaussian process is parameterized by two functions, the mean function and the covariance function. And if we evaluate at location xt, then the expected change, the change of the mean function is a stochastic change, because you don't know yet what you're going to get, but you know what you get is Gaussian distributed. And so the change is some random Gaussian variable times some object which I call the innovation function because of the non-parametric corresponding concept to the innovation in a finite dimensional Gaussian model or in a Kalman filter model. And the change to the entropy is a deterministic change. So I'm not going to go into detail what that function actually is, you can evaluate it. And if you're interested in this, then I can shamelessly plug my NIPS paper this year, which is a lot more detailed on this point. And I will also talk about this next week at the engineering department, so if you're interested in this, please come to my next talk. Okay, so a much easier way to think about this is, here's another picture. This is our Gaussian process belief from before, with our mean function and covariance function. Now, if we evaluate here, then we don't know yet what's going to happen, but we know what our uncertainty is going to be afterwards, and we have a belief over what our mean function will be afterwards. It'll be something like this. This one is the most likely change, and these other ones are less likely. We know that there will be a lot of change in this region to our belief, less change over here, very little change over here. And if we evaluate over here, where the heuristic thought that's a good place to evaluate, then we'll get a little bit of change here because we already kind of know the function, and less change here and almost no change over there. So that's the way we're going to think about this. Now, this is only the change to the belief over the function. How does the belief over the minimum change as we evaluate somewhere? So one convenient aspect of EP is that once EP has converged, and I'm hoping I'm not saying anything wrong, the EP's answer becomes locally independent of the value of the messages. So the first derivative of that answer with respect to the messages is 0, and you can do a first order expansion of EP's answer with respect to just the input parameters mu and sigma. And yes, so we'll do just that. So we'll predict the change to the belief over the minimum to first order. Since it's a stochastic change, we have to use Ito's lemma, and there's actually a second order term showing up as well. If you can do that, not a big problem. This is actually the easiest term in there. And then there's a stochastic change as well, which we have to integrate out. So we do that in the trivial way. We just sample a number of standard Gaussian variables and just do this calculation s times. I think we do it 200 times, something like that. So do a Monte Carlo integration over to predict the entropy or the relative entropy from the base measure after evaluation. And then we just maximize that function. So we just maximize our expected information gain at any location, like as a function of where we evaluate the function next. One nice property of this, the fact that we do this as a Monte Carlo integral, is that there's actually nothing special about the fact that we take the log loss here, the entropy. So if you don't like entropy and if you think some other loss is a better measure of uncertainty, then you're free to choose that and just plug it in and it'll work just as well. It's just a matter of what function you want to evaluate. Okay, so that's basically it. That's the entire algorithm. Here's a sum up in a pretty picture. This is our initial belief over the function, which I've shown you several times now with a few samples from it. We would like to be able to turn this belief over the function into this blue belief, this solid blue belief over where the minimum is on this domain. Can't do that in an analytic form. So instead we're going to use approximate integration using expectation propagation. If we could do this on a grid, we would get this dashed blue line, which is quite a good approximation. But we can't do it on a grid because we are in a multidimensional space. So we'll replace this grid with a number of sample points on a random non-uniform grid. And these are represented by these blue circles here. There's one up here as well, and one down here. You see that those points are not exactly on the line. That's because we're sampling the points, but we're analytically evaluating the measure. So there's actually a stochastic error in the width of each bin, which gives us these variations in here, which would go to 0 if we would sample infinitely many points, which obviously we don't do. But I think this is a sufficiently good approximation in light of what I'm going to tell you next. These two lines up here, the red and the blue line, these are the predicted changes in entropy up to some additional constant as a function of where we evaluate the function next. So, yeah. And the red line is, sorry, the blue line is what you would get if you ran this using EP on this grid. So that's supposedly much better approximation. And the red line is what you get from the samples. And you see that those lines are not the same, but they are close to each other. And I've also again marked the points where these functions become maximal. So this is the value, the point where these two algorithms would decide to evaluate next. And you see that it's in a different region than where expected improvement would evaluate. This is because this region over here, yes, is highly likely to contain the minimum, but it's also a region where we already know the function quite well. So these algorithms have decided that it's a better idea to evaluate over here, where there's also a considerable mass for the minimum to be there, but there's more to be gained by evaluating up here, because we're more uncertain about what the function is. Another interesting thing to note is that in the corner, at the boundary of the space, even though there is a considerable probability, a finite point mass probability for the minimum to be over there, this is not necessarily an interesting area to evaluate because, so this function goes down here, because if you evaluate right at the boundary, then you're sort of throwing away half your information gathering ability because you're learning something about the function outside of the box, which you've decided you're not interested in. So it's actually a better idea to evaluate over here, where you learn something about the function at the boundary, but also learn something about the function at other regions towards the left. Okay, that's the idea for the algorithm. Now I'm going to show you some plots and about how this function works. But maybe I should take a short break and ask whether you've got any questions. Yes.
So if I don't want to have to restrict myself to a bounded set, what does this extend easily or not?
It extends, but it doesn't extend easily. So what you do is you need to have a proper measure of where the minimum is. So that will necessarily then be non-uniform. And you'll have to do another round of EP, iterating between your GP belief and your belief over the minimum, to get a consistent belief over what the function is and where the minimum is. So you're having this belief over the minimum induces a change to your belief over the Gaussian process. So if I had, let's say, a Gaussian belief over where the minimum is, so starting over here, becoming maximal over there, and then moving back down again, then that would also mean that I think this function is low around here and high around here. And you have to get that in.
So you're sampling these points, right, over this space.
Yes.
Now, the number of points that you sample, of course, is a computationally expensive operation. And if your the function evaluation time is not that much, you really don't care, right?
Yes. So that's a point that, especially that so there's something about optimization that if what I'm doing here is I'm essentially solving another optimization problem just to decide where I'm going to evaluate the function. So if your function is something numerical on your computer, if you're, I don't know, if you're maximizing, if you're trying to learn some hyperparameters for Gaussian process regression or to learn a neural net or something, then that's not the right approach at all. Then you should just use something really cheap, which does have some, I don't know, actually just restart a few times from a sampler, run some local optimizations and just do that. That's then, so if the function is cheap, then suddenly turns into a kind of a boring problem because then you don't want to use anything smart.
No, but my question was that there's a middle ground, right, where the function is not very cheap to evaluate, but it's not very hard to evaluate as well. Like the time taken to do this analysis is sort of roughly in the same sort of order as your function evaluation time, and then both of these things should come in to tell you how many times you should sample here.
Yeah. Okay, yes. So what I can tell you is that for the experiments I'm going to show you, we're using 50 samples, and deciding what to evaluate next takes about a minute. So if you are working in a chemical lab, then I think waiting for a minute is fine. And maybe you're even willing to wait for an hour, and then you can run more samples. And if you're doing something where evaluating the function takes 10 seconds, then this is not the right approach.
And the other is batch. What about not just 1 point sample, but if I have a machine, if I'm in a chemical lab and I can do 10 sort of evaluations in one go, what would be the 10 best places I should look simultaneously? Okay,
so I haven't thought about that yet. I think that will again turn into a dynamic programming problem, right? Because you can't just take the 10 local maxima of this function, right? Because that's not going to be the right thing.
Right, again.
Yes, yeah. So that's definitely a harder problem. So you have to think about that. But so I don't know how frequent these problems actually are. It could also be that you just run an experiment, enter the number into your computer, and it tells you, like, go away, have a coffee, I'll tell you in 3 minutes what to do next. Okay. Yes?
I'm not sure about entropy being a good approximation of uncertainty of the maximum, because we perhaps want to take use of metrics on support. For instance, take something like variance on posterior distribution of maximum would be better. I mean, maybe for computational reasons it's unfeasible, but.
The philosophical argument behind the entropy as a good measure of uncertainty is a lot more shaky than the philosophical argument behind probabilities and Bayes' rule for inference. So if you disagree on the log loss as a measure of uncertainty, then yes, then maybe you have some other loss that you want to use. But this algorithm is actually quite agnostic to this kind of choice. So there's just a function h, which takes in the distribution over the minimum and does anything with it, and you can predict how it's going to change. And because we solved this integral by Monte Carlo simulation, so we just sample the number of numbers. As long as you can evaluate your function, you're fine. So yes. So even though I've decided to call this algorithm entropy search, you might decide that you want to minimize some square loss on something or whatever you like, right? And then you just plug it in, and maybe it gets some better answers. I don't know. But then, if that's the case, then we have to start arguing about whether entropy is the right measure of information. And so that there are larger giants to ask for what are the right answers for that. I'm not the right person for that.
So one.
Sorry, Sebastian?
Yeah, one question. So if you could, instead of just evaluating the function at a single new point, if you could sort of evaluate it on a measure, so you could propose a distribution and evaluate the function integrated under that measure, could you use that to your advantage?
So let me give a slightly more specific answer than to this very general question. If you can evaluate the derivatives of the function to any order, which is something like sort of a locally larger region, right? Okay. So if you evaluate a function up to second order, then there's a second order Taylor radius around the point where you sort of learn about the function by evaluating there. Then everything just plugs in right without any problems, because differentiation is a linear operator and Gaussian beliefs are conserved under linear operators. So you can just do Gaussian process inference with functions and the derivatives as well. it's harder if you get integral information about the function. Then the maths doesn't just fit so nicely. So you have to think about exactly what you're doing there. It's the same goes for, of course, if you do Gaussian process inference and you don't know the kernel parameters yet, so then of course you can learn them, but you sort of have to be careful what that actually means for what you're optimizing now, right? Because that's not part of your calculation anymore, or you're going to predict where to evaluate, or if you have observations which aren't actually Gaussian or don't have Gaussian noise, if you have some more complicated likelihood, then you have to do something approximate. But we all know how to do approximate inference with Gaussian processes, right? So it's not a sort of, it's a widely used field. Which means?
So the question was, so how would the results sort of change if you consider completely discrete spaces, for example, a hypercube, right?
Mm-hmm. So as long as your discrete domain, that your belief over that discrete domain can be described by a Gaussian, so as long as you have finitely many points and you have some measure of covariance between them, and that's the only other information you have about them, then everything filters absolutely without any change actually becomes easier, because now you just have finitely many points to consider, and it's just you just count through and evaluate at every point what's the best thing I can do. Right?
What if this expected change of entropy function, which you want to minimize over x, is actually harder to minimize than your function in the first place? So you basically took a minimization problem and turned it into
yes.
another maximization problem.
So that this the same answer as before. If you think the function is really cheap, either cheap to evaluate or cheap to minimize, then this is not the right approach. And I think you should really keep separate local optimization problems where you want to have a really cheap, fast algorithm that does something reasonably smart but not too smart and just returns an answer within a millisecond. So basically some sort of quasi-Newton or variant of that or conjugate gradient, so sort of you build a local parameterization of the function and then evaluate whether you think that local parameterization is minimum. And the real optimization problem where the task is there's something complicated which is expensive to do and I want to do it right. And then this is, I think, a better answer. And if you're just training some machine learning method and you want to minimize something, then this is not the right thing at all.
And you explained this to me quite earlier. I really see the oil field versus some in-memory optimization problem. And you take this any day if you can save one more hole to
one more rat to kill.
Yes, exactly. Yes.
One more patient to save.
Last, but maybe a slightly stupid question. So this is highly dependent on how I pick my Gaussian process prior.
Yes.
Did you say something about that?
Not yet. I actually have a backup slide at the end that I can. Well, actually, I can just do it now. Let me just move through this very quickly. And okay, if you don't like, so of course you have to choose your prior. Now, I hope most of you know that Gaussian process priors are actually quite a flexible family of beliefs. Yes, having a Gaussian belief is restrictive, but you can actually do a lot of really smart things with Gaussian process regression. You can choose kernels which have scale mixture distributions over the length scale of the function. You can choose sums of kernels so that you have different length scales in your belief, and so you can say something like, I think the function is sort of globally stationary, but varies on a very wide range, and then in the local region where I'm interested, it sort of has some more local structure, and you can do that kind of stuff. If you know that so I think the typical optimization problem is you sort of know that the function is large around the edges, right? You sort of it's large somewhere here, but I don't really know what the structure here is. Not just a parabola, but it's something more complicated in there. Then what you can do is have a parametric mean function, and so for example polynomial or any other I think it's called an effective kernel, which takes care of the overall trend, and you can infer that at the same time in closed form in your Gaussian process belief, and it just plugs really nicely into this kind of framework, and it'll just impose a global covariance that says, like, if you evaluate the function here, it's large there, then you also think it's large over there, something like that. Then we can have non-Gaussian likelihoods. So you imagine that you know that your function is strictly positive, but it takes really large values somewhere, then you might be interested in just a log of that function because it's a lot better behaved. Of course, if you have a Gaussian noise on the function value itself, then this is now a non-Gaussian likelihood, and you have to do some approximate inference. We did some experiments on that. The simplest thing you could possibly do is just a Laplace approximation on the likelihood, and it's already a lot smarter. You can obviously learn the kernel while you learn, so you can have a Monte Carlo sampler running in the background that constantly updates the belief over the function, the kernel parameters, things like that. You can plug in relative observations, as I already said. So, of course, it's a restriction. Having a Gaussian prior is not the most general prior you could have, but I think it's a very flexible class to describe a function in particular because you can think a lot more flexible about the function you're interested in by just thinking about kernel parameters. So you can say, I only know the length scale of the function, but I don't know at all what it looks like. Or I know that it's periodic, but I don't know the periodicity, the frequency, the wavelength, things like that. So, and my answer is, okay, so you could write a number of papers on all sorts of approximations that do the same thing, and maybe we have to do that to tell it, to explain it to people who are in applied fields, but I think as machine learners, we kind of know that it's actually quite a flexible inference framework. Okay, so let me just briefly show you some results. There are, most of the functions I'm going to show you are low dimensional. One thing I want to point out at the beginning is global optimization is very hard. If the space that you're looking in has a high volume, high effective volume in terms of the scale of the function, then even if you're extracting information efficiently, if there's lots of information in there, you still have to evaluate a lot. So the experiments I show you are on low-dimensional functions, 2- and 4-dimensional. And if your function is higher dimensional, then either you have to assume that the function is very simple in some sense, or you have to assume that you know some sort of transformation, right? Some sort of latent variable concept where the data you get to see is high-dimensional, but what's actually going on is a low-dimensional problem. And then that's another inference problem you have to take care of, and I'm not addressing that at all. Here is a classic optimization problem known as Browning's polynomial. A lot of people know Rosenbrock's function, which is this banana-shaped function. Browning's polynomial is sort of a variation on that. So this is a function which globally also looks like a banana, something like this. But there's another polynomial on top, which creates local, as a local structure, which actually uses global optima. So in this particular box, the function has 3 global optima, one here, one there, and one up here. And we're trying to just find whatever the optimizer thinks is the global minimum. As Tor pointed out yesterday, of course, this algorithm doesn't actually take into account that there might be several global minima, but it sort of degrades gracefully. It'll just think that there's one and hop back and forth between them and learn 3 spike distributions that says it's either there or there or there, and I don't really know yet which one it is yet. It's unclear how you should evaluate the performance of a global optimizer. What we're doing is we're trying to minimize entropy of the belief over the minimum. That's not something I can plot because the other function doesn't provide that. What seems to be accepted measure of performance in the community is the distance of the difference between the function value at where the optimizer thinks the global minimum is and where the actual global minimum is. The reason for this kind of measure is that if you're globally optimizing a function, you usually don't actually care about where the minimum is. You just want to have a location where you'll get a good function value out. So even if it's somewhere completely different, as long as the function is low there, that's important. So what I'm plotting here is the thing on the log scale. The blue line is us, that's entropy search, and the red line is expected improvement. So that's, to my understanding, the state of the art. There are some other Gaussian process global optimizers which use other heuristics, and there is a PhD thesis by Dan Lizotte which seems to argue, although with a big error bar, that this is the best thing you can do. And we see that we're something like, depending on how you want to read this plot, so these are 10 experiments each, and the thin lines are the experiments, the thick lines are the means. And I would argue that we're, well, maybe 1.5 times to 2 times faster in our convergence than the other algorithm. Here's another function, which is in some sense sort of orthogonal to the other one. This is Goldstein's and Price's polynomial, another 2D function. This one has a global minimum which is really peaked. So the other one was sort of a wide, smooth function, and this one is one with thin trenches that you have to fall into and then figure out where the minimum is. And there's just one down here. So we do that here again. This time we didn't do as many experiments because I did this on Friday before I came here. We do 50 evaluations, again 10 experiments. Blue is us, red is the other method. And if once you're below 10 to the minus 1, sort of around here or so, then you're basically in this region, right? Then you've found the global minimum. And after 50 evaluations, I think I've counted this to be 7 of our algorithms out of 10 have managed to find this optimum, while only 1 of the other algorithms has found it, and also just at the end. So yeah, this is not sufficient to say anything about how much better we are, but it's definitely better.
Why? I imagine the same question. Why do you get worse sometimes?
Because you're still exploring, right? So sometimes you do you get some sort of evaluation around here, and then you do something over there, and because you're evaluating with noise, that's it. You're evaluating with noise, so you actually your approximation moves up to the function, right? And you actually think the minimum is at a different location. And also you have just finitely many points, so the GP does something in between, which is not always the right thing. So it's not necessarily building exactly the right model for this function. So you could say that I've evaluated here and I've evaluated over there, and due to these 5 evaluations I've made, I think that the function looks something like this, but in fact there's actually this hump in between which the GP hasn't seen yet. And then it'll put it'll estimate that this should be the best point, but if you actually evaluate there, which you haven't done yet, you'll notice that this is not the right location. Frank?
Maybe you said that already, but when you evaluate your f hat for your search method and the other expected improvement one, do you compute it in the same way? Or?
Yes. So both algorithms have a GP belief, and they have the same GP prior, with the same kernel and everything. And they both construct their guesses for where the minimum is by doing some sort of simple, by like random restart local optimization of their own mean function. So this is some way of writing. This is not where the function wants to evaluate next, but it's the answer to the question. If you have to stop now, tell me where you think the minimum is, and it just tells you where its own global minimum of the mean is.
But for that, you would have to estimate p mean again, if you wanted to do it like in Bayesian decision theory.
You have to evaluate. Okay.
Well,
so yes,
like
you're right. Yeah. So if you wanted to, that's true. So if you wanted to really do this right, then yes, then you should evaluate p min again and tell me where this. Well, yeah, where the minimum, where the function is most likely to have its minimum, maybe. Yeah. So I don't do that partly because I want to have a comparable output between those two algorithms. Yeah. Also partly because I just wanted to have a quick number out of the algorithm and didn't want to run another function on top of that. Yeah. But maybe this is actually, this is maybe a fair comparison because it just tells us how quickly these beliefs converge. Yeah.
You started your talk with bashing the heuristics. Where are the heuristics on this plot?
So the red line is the heuristic.
That's one heuristic, but it's not a popular one, right? For example, Nelda meets search is implemented in MATLAB, or the Powell's algorithm is probably the most efficient derivative-free optimization method, okay. Right? So, where are these heuristics?
So they are not in this plot, obviously, because we also haven't run these experiments yet. For 2 reasons. One is that the nice thing about this is that the other algorithm is also a Gaussian process optimizer. So a lot of comparison issues about the prior fall out. So we don't have to worry about, do we have a sort of, does the prior help us to somehow make it easier for the algorithm by using the prior? The other thing is that the paper hasn't been published yet. It's actually just about to be submitted for our next workshop, and we haven't done more extensive experiments with a large number of other algorithms yet. But this is the sort of, I know this is the sort of work where any reviewer will have another suggestion for what you should compare to, and will hopefully compare to, 10 other algorithms, and we'll see how it works. But so this is conjecture, but I'm pretty much convinced that an algorithm which doesn't have a prior cannot be this efficient, at least not on a general class of functions, because you'll invariably have some functions which have a structure which is somehow not taken care of by the implicit assumptions of the other algorithm, and it'll just behave very weirdly. But yes, I'm not saying that that's actually the case. So we'll have to do more experiments.
So how did you choose the covariance function here for these problems? Are there some heuristics about the length scale?
Yes.
Or did you even take it maybe a polynomial kernel because it's a polynomial function?
No, so we choose for this one we choose a rational quadratic kernel, which is a scale mixture over square exponential kernels. And we chose, so for these we just set the parameters by looking at this plot and saying this should be roughly the right parameters and just plug them in. Because we are comparing to another algorithm which has exactly the same prior. So all these results are modulo the kernel parameters. What we do have is some initial experimental code for an algorithm which while it does these decisions runs a slice sampler on the kernel parameters, and you get your first 3 evaluations or so, and it gives you a distribution over where actually it starts from it has a proper prior with the kernel parameters, so it starts with before you even get the first evaluation. You sample from the prior, get a distribution over what the kernel parameters are. You construct a mean Gaussian process out of that with a mean function and a mean covariance function, and then sort of suck everything through and take everything in expectation. And that seems to work quite well. At least it converges to a nice sort of quite close distribution of kernel parameters relatively quickly. So for a 2-dimensional function, it converges within 10 evaluations or so of the function. But that's sort of a next step already. It's another question of how much you can do with kernel parameter learning. Okay, so here's one last function which I can't plot because it's 4-dimensional, and this is a case of global optimization is very hard. So this is a function called shapeless foxholes. It's another polynomial, and you can think of it in as a 4-dimensional version of the following situation. You have a flat surface, like a meadow somewhere here outside of Cambridge, and there are rabbit holes or foxholes in it, where you sort of have little holes in the surface, which, well, they're polynomial, but they look a little bit like inverted Gaussians. Just that they're not asymmetric, so they're sort of more sort of trenches everywhere. And so the idea behind that function is that an algorithm which is not very smart is going to get stuck in one of those holes. And they're actually all in a reasonably close region, relatively close to each other, of sort of diameter, well, actually 10. And you see that something not quite that bad, but in this direction happens to expected improvement, that after the first few evaluations, it nearly always falls into one of these holes. It's not always the same hole, which is why the distances here are different. But it always sort of starts, because expected improvement is in a way more greedy, because it just wants to get the function value down really quickly. It sort of starts exploring, but if it finds a hole somewhere, it starts exploring in that hole for a while, until that hole is sort of understood. And then it knows that there's not much more to gain, then it'll start exploring elsewhere, which is why it crawls out of this hole again over here and then sort of settles into this machine. And entropy search doesn't do that, because there's no such concept. It's still it's a global problem, so it considers where should I globally evaluate. And yes, if I found a region somewhere where there seems to be a low function value, that's great, but there might be other regions which I'm more interested in to evaluate in. So we just sort of smoothly decay, and then eventually you do discover regions which look really good. And this is this area over here where, again, I think I've counted these lines, and it's sort of 6 out of our 10 algorithms which have here. So this black line is the region, once you cross this, you're in the right hole. And so this seems to have happened here more quickly than for the other method. But this is more of this plot is more to show the sort of different kinds of behavior of these algorithms. It's not necessarily a pathology, because it's sort of it's about what you're actually trying to do. This thing is trying to quickly get to learn about a region which seems to be low, and this thing learns to efficiently tries to efficiently learn about the function in the entire region. Okay, so here are the conclusions. I argue that current contemporary global optimizers do not have an information gathering view. So in that sense, they're not information efficient. That doesn't mean they're bad, they're just not information efficient. And if you want to construct an information optimal global optimizer, then you're faced with a number of intractabilities, but you can construct an approximate information greedy optimization algorithm by committing to a particular prior on the function, solving the integration problems on a discrete grid with approximate integration methods like EP, taking care to do the approximation of a continuous function with a discrete number of points right, and then using the probabilistic model of the function to predict how this belief is going to change and how therefore the uncertainty over the location is going to change as you evaluate at a new location, and also throwing out every horizon problem and just doing a greedy search. This kind of approach is quite general in the sense that it works with a large class of functions, everything that can be described within a Gaussian process prior. It works on discrete and continuous settings. It works with and without noise. It works with and without derivative observations. They all just sort of plug in, at least as long as the noise is Gaussian. If it's non-Gaussian, you can make approximations. But nevertheless, global optimization itself remains a fundamentally hard problem from an information theoretic point of view. And that is a point on not necessarily the obvious dimensionality of the domain, but on the complexity of the function itself. And that's something that sort of quite neatly falls out of this Gaussian process prior. If you want to optimize a function that you know has a very large, so if you're optimizing a parabola in a 1,000 dimensional space, then this algorithm will actually do this quite well. And it won't worry too much about the fact that it's a 1,000 dimensional problem. If the parabola is sort of completely filling out your domain, and if you already know that it's parabolic. Because it'll just very quickly learn the parameters of this parabola with the right kernel and just converge very, very quickly. But if you're trying to globally optimize a one-dimensional function, which has length scale 0.1 on a domain that has size 100, it'll take roughly 1,000 evaluations to find this minimum, just because the function is so hard. So this is a question of how to very quickly extract information from the problem, and if the problem is complicated, then it might still take a really long time. Okay, so I said that the paper hasn't been published yet. We're about to submit it to an ISP workshop, and there will hopefully be a much longer version in some journal at some point. If you want to have a copy of either of those papers, please send me an email. We will be very happy to send you one. Okay. Thank you.
Okay, I think we have time for a couple more questions.
Great.
Yes. Is it me? Or
Yes, I think it's you. The latest John.
so have you thought of? So I think the main problem here is trying to figure out that density over where the minimum is based on the Gaussian process, which seems to be a very, very hard problem. Mm-hmm. And it's very similar to other hard problems with Gaussian processes are not particularly easy for. And so would it not be easier computationally to treat the minimum as an explicit hyperparameter of the function class that you're considering? So the generative model would say that I draw first where my minimum is and what the minimum value is. Mm-hmm. And then based on that, I drew a function which always, or at least most of the time, will have a minimum at that point. Yes. It can construct like Gaussian processes, which will do that using the mean function and covariance function. And then my data is generated from that function.
Yes. So I guess that's a question that has not really a correct answer, right? So there are algorithms there are paradigms which use evaluations with derivatives to construct outer envelopes on the function, and then you use sampling from some prior that might be a Gaussian process or something else to construct functions which still fit into this constraint set. There was something on the archive just 2 weeks ago, I think, which doesn't do optimization, but just sort of tries to learn these kind of models. My impression is that those kind of models have a much harder inference. So you usually have to run a sampler for a long time to get some reasonably good exploration of the function space. Something I really like about the GP approach is that we are not restricting the expressive power of Gaussian processes at all with this framework. So you at the end the GP makes a Gaussian prediction over these 50 points that we've sampled, and then we just run EP on that without thinking about where it came from. And that means that you can choose your kernels, you can make all these general statements about the function, and still do roughly the right thing afterwards. So I'm not sure how well that filters through with other inference algorithms for functions. It's also one thing that I think is hard with these other methods is to predict how your belief is going to change as you evaluate somewhere. Right? Because you have to, so basically what you have to do is you have to sort of take samples over what the right function might be, then evaluate for every point where you want to evaluate, you'll have to then like for each sample, you know what the answer is going to be if you evaluate there. Then you have to run the sampler again to predict what you believe is going to be afterwards.
That you can solve by using the symmetry of mutual information and stuff. But anyway, we can talk about it later.
Okay, so yeah, I'm not sure I understand that point, but
Yeah,
so
it's not an easy point.
yes, yeah.
Last question.
This is just a small question. Did you actually tell us what expected improvement is?
Okay. So I did that in the very first slide. So it's the expected distance or difference between your best guess so far and the evaluation at the next point. So where is that initial slide? Here. So what this says is this is your current best guess. That cross is the best number you have so far. If you evaluate at this point, then you'll get some other number, which is Gaussian distributed, with a one-dimensional Gaussian distribution. And that number will have a distance from this thing here, and you'll bound that by 0. You say, like, if it's larger than the value I've had so far, then I don't get anything. And if it's less than that, then I'll gain something from it. What's that number in expectation over the Gaussian distribution?
I see.
And the nice thing about this is that you can do this in closed form, and it's reasonably cheap. It involves evaluating the GP mean, the GP marginal at this one location, and then calling an exponential function and the error function. So it's really cheap.
Yeah. Thanks.
All right, can you talk to him afterwards? Okay, let's thank